Hello, welcome to lecture 12, video 12 in the lecture Advanced Mathematic Modeling. Today I want to introduce variable transforms of random variables and the application for the associated probability distributions. This is an important technique which will on the one side help us to with the computer to generate new distributions or to generate random numbers from new distributions, and also will help a lot if you want to transform between different distributions. So what's the idea? So let's assume we have a continuous random variable. So continuous random variable x with a probability density function p of x. And now assume we have a function f which transforms the variable x to another variable y. Then y, of course, is also a random variable. And this random variable has a distribution. And now we ask, what is the distribution, which we call q of y, the probability distribution of the new random variable? We can depict this problem graphically. So here we have our continuous random variable x. Here we have p of x, that's our function. And now we make our transform. We go over from x to the variable y. And now we want to know what is the function q of y, which might look a little bit different. And so that's the problem. So now how can we calculate this q of y? And here you have to be careful. The first idea that you say, we can just say this q, since y is a function of f, so we could assume that we write down something like q of y of x and hope that this would be the correct function, but this is wrong. Yeah, this would give you the wrong idea. And to get the right idea, we have to see what is the probability that a certain event happens. And the probability in a continuous variable means we need here a small interval, the x, and the probability for a random variable in this interval is proportional to the size of this rectangle. And now under the variable transform, the probability cannot change. So now we transform this interval to some interval here in dy, and then the area under this rectangle, these two areas must be the same, because the probability is independent from the transformation. So the main assumption is that we write the probability p of x dx, so that's the area of this rectangle, equals the probability when we have transformed our variable q of y dy. Now there is a subtlety with the signs. I mean, when we say here this dx is increasing, or by the variable transform maybe dy is negative, and then we have a negative area and so on. So it's more safe if we take the absolute value to really have probabilities. So that's the thing you have to keep in mind. Everything else is now just application and calculation with this. For example, now we can solve for this q of y, and then we obtain our formula q of y equals p of x of y times now the absolute value again of the derivative dx over dy. And but this here, this formula works only if we can calculate this x of y. Maybe make here a graph of the function. So this is our variable x, and that's our new f equals f of x equals y. And if this is a invertible function, yeah, then we can of course calculate here the inverse x of y. So x of y, maybe we should write here. Where should I do it? Maybe I just write it here. Let me think. Oh, let's write it here to the side. And we can do this if the function is invertible, if x is invertible, so that we can write x is the inverse function applied to y. Only then we can use this formula, because our function gives us y as a function of x, but here we need to invert this, because here we need to calculate x as a function of y. So for such a function this could work. Examples would be ln x would be square root of x, x to alpha, exponential of x. Yeah, so this would be all functions which are invertible. But for example, if you have such a function, this is not invertible, because now for this y we don't know which was the x, so you cannot really know the x from the y. So what do you do if the function is not invertible? So either you do this for, sometimes you can use cases, for example, if there's an area where the function is increasing, another area or regime where the function is decreasing, then we separate the y, and now you can make clever arguments and separate the x values in the smaller and larger regime, and then you can combine this and come up with such a formula if you carefully combine these two sides of the function. In general, we cannot use this simple formula. So what you can use in general, we can write down this q of y with the Dirac delta function. So we can say q of y is the integral. We have to integrate over all x values to find here the q at a certain position y. And now we take the delta function of f of x minus y. This delta function takes care that we use only this y which really belongs to f of x. So we here by this integral we sample over all of x. We have to weight by the density p of x of this x value, and then we multiply by these functions to make sure that from all these x values only dy value is selected for which f of x equals y. So this is the general formula And if you multiply this on both sides by dy, and then you see this integral we can replace by y, q of y, yeah, if you just multiply this here on both sides by dy and integrate here, then you come back to this formula we had here above. So, but this is not something we will use here in the lecture. In the lecture we take only examples, and that's the important case, that the function here is invertible. So examples like this, and then we can really use this here. But first, before I now show how to apply this method in some examples, I want to give you a brief overlook for the Dirac delta function for people who've never seen this, because this is a very useful function, and then we come back to this here. So what is the Dirac delta function? And maybe the most intuitive idea is to say this Dirac function is a function which is the limit of a concentrated function. Let's say we have here a variable x, and we have here a Gaussian, or let me see, maybe I call it h of x. And so this could be like really a Gaussian function, like as we introduced in the Gaussian distribution. And this has a certain width sigma. And such a function expresses a variable which has high value around 0 and small value far from 0. And now we can see what's happening. And we want to have the integral under this function as in the Gaussian. We want to have the integral of this h of x, the x equals 1 from -infinity to infinity. So as in the probability distribution. And now how would this function h look when we reduce the sigma? Then probability has here a higher value, or this function h has a higher value around 0 and is a bit more narrow. And now we can reduce the standard deviation or the sigma even more. And then we end up with a function which basically has all density around 0 and nothing outside. And then we say the Dirac delta function, we say, is the limus, when the sigma goes to 0 of this h of x. And yeah, I should have given this an argument sigma so that you see here the width of this distribution. So basically this means we have a distribution which has value infinite at 0 and 0 some everywhere else. So delta of x equals infinity or 0 if x equals 0, and here if the function is 0 if x is not 0. So if you make this limit, then this function has only a contribution when x is 0, and then the value is infinite large, and if x is not 0, then the function is 0. But then you see, and we assume that if we integrate this delta of x dx over -infinity to +infinity, this should still be 1. So now you could say, okay, that's not a real function, because yeah, we have it's always 0, and then it has this jump here. So actually, we such an object mathematically, it's a distribution. So it's the delta distribution, and distribution means it's an object for which is only defined by its integral. So the integral over this delta of x is really defined. Yeah, but in modeling we can sometimes be a bit sloppy and say that's just a function which is 0 everywhere, but at x equals 0 it's infinite. And this is a very useful function to describe something which is concentrated at a certain position. For example, if you want to describe a concentration of some molecules, and we say we have molecules only at some point here x0, and we want the concentration of x. How can we do this? This function is defined at has the singularity at x equals 0. How can we write it as a singularity at x at a different position? And we write this as a delta of x minus x0. So by simple transform, by shift, we can obtain a distribution at some other point. And here you can see this distribution. And since the function are normalized like a distribution, we can also understand this data distribution as a probability distribution. So this would be, this is also a probability distribution. And describes a random variable which is localized at x equals 0. So, and then what is, and this is really a distribution. I mean, like we said, that's maybe not really a function, but when we want to get a probability, we need to integrate over distribution, and integrals over this delta of x are well defined. So this is really a probability density. So what would be the cumulative distribution of this? What is the cumulative distribution? CDF of the data function. So if we now integrate delta of x dx bar from minus infinity to position x, then you see this is either 0 or 1 if the value x is larger than 1, and 0 if x is smaller than 1. So if we have here the delta of x, which is like this, and of course this is when I want to visualize this, I sketch here a value with a finite sigma. And so what is the cumulative distribution? P smaller of x. So that's a function which is starts from 0, now makes a jump to 1, and then stays 1. And this is also what's called h of x. That's called the Heaviside function. So you see the derivative of the Heaviside function is the Dirac delta function, and this function here is very useful to express all starting or jumping processes, and the Dirac function is helpful to understand all localized functions, and they're related by integral or derivative. And so this Dirac function helps a lot in many calculations, so it's used in all places in modeling. For example, we can generate a translation or shift with horizontal translation or shift. If we have, let's say we have a function f of t, and we integrate this function by a Dirac delta function which is localized at some other point, at some point t. Now if we integrate this over dt, then this function just picks us the value of f at capital T. Yeah. So if we have a function and we want somehow with some formula to pick the value at a certain point, we just integrate over a shifted Dirac function. And some other useful application of the Dirac function is for variable transforms, and we have seen this here. Now maybe if you didn't or haven't seen the Dirac function before, now this should be clear. If you want to make a variable transform from function p of x to function q of y, and then this q of y, we integrate over all p of x, but here with this Dirac function we take sure to take only these values of p of x, so that f of x equals y. Yeah? So it's a very useful function. So now, since we have understood this, but we know we continue with the more simple formula where we assume our function is invertible. And now I want to give you one or two applications of this in order to help us generate random numbers. But with this we do in the next video. For now, thank you.